So this is the work in collaboration with a few other folks. So I want to acknowledge right up front, and they couldn't be here. Eric, Anirudh, and Raju. Eric and Anirudh are political theorists and economists, and Raju is a computer scientist, and I'm in city and regional planning. So it's a very interdisciplinary team that we are working with here. So some of the, I don't know if I need to motivate this work. About 30% of the world's population live in urban areas, in irregular settlements, whether you call them irregular, informal, favelas, or whatever that might be. That's close to about 1 billion people living in these places. And the places that we are interested in, the place that we are interested in today is Bangalore, one of the rapidly urbanizing city in India. And the official estimates are that there are about 1.5 million people living in these kinds of settlements. It's a gross underestimate. There about the expectation is about 600 or so such settlements exist. Out of 9 million people, about 1 million people live in these kinds of areas. And there is a little understanding about how social and political networks operate in these areas and how we can actually sort of figure out what to do about these areas. A few years ago, a famous paper sort of roiled the planning world, and this was written by Ananya Roy, who was to be a faculty member here, no longer here, I think, called Why India Cannot Plan Its Cities. And she places the blame completely on informality. So she essentially says that pretty much all of urban institutions in India are informal, whether it's the economy or whether it's the political networks or other kinds of things. They operate outside the formal sector, and therefore any amount of planning as she conceives it as a governmental intervention will not work and does not work. And one of the ways we are trying to see is that if that is true, and if that is true, what kinds of institutions are actually being built up in these areas that obviously about 1/3 of the people live around the world. Okay, so my task or my remit in this whole process is to essentially give the political scientists a sort of a sampling frame as to where they would go out and survey these places, what kinds of household surveys need to be done, what kinds of physical surveys need to be done, and so on and so forth. This is me and Raju working together in this area. Though I'm also an institutionalist, I'm interested in how these neighborhoods actually work in an urban system. So we start out with a sort of a medium to high resolution images from Worldview. So Digital Globe gave us the data sets. We then combine them with other ancillary data sets such as OpenStreetMap and other kinds of data that is available. And we then try to do a standard land cover classification, not as complicated as what Ron had pointed out, because we are more interested in what happens at a neighborhood level, and then see what we can, how we can validate that information. And those are the results I'm going to present today, though there are other aspects to these projects that are also interesting that we could probably talk about if we have more time. So the place is about 2,000 square kilometers wide at a 2-meter resolution, which is about 2,000 square kilometers wide at about a 2-meter resolution, and has about 84 images that we needed to mosaic and sort of fit them all together, make sure that it lines up with the OpenStreetMap, and it's a complicated and time-consuming, time-intensive process, and I wouldn't recommend it if you don't have to do it. One thing that should be noted is that there are significant data gaps in these ancillary data sets that we've collected, including roads and other places. And so we had to either fill it in manually or assume that it's an error in the data sets that we're going to live with. And then the standard pan sharpening procedures. So the standard classification that we did was through with thresholding, just to get the basic ideas about where the vegetation is, where the water is, and where the bare soil is. But what we are more interested in are the buildings. So for this, we needed a more elaborate technique. And to do this, we use what is called a morphological building index. And you essentially do a difference of opening and closing of images, taking on the pixel level. And you use a structuring element, which is rotated at different angles, and then you average it out, and you get an index that looks on the right side of the image. So to essentially get a indicator of what where the buildings are, we want to separate out buildings from other types of urban features, such as roads and those kinds of things. So what you can see in the red over there are the areas that are already being designated as informal settlements from previous surveys. And what we can see on the blue circles are the candidate locations that we think would be right things to classify as settlements. When most of them have to do with the kinds of textural features and also the kinds of spatial arrangements of these buildings. So what we then do is to go to a 100-meter hectare level and calculate these kinds of features including density of the roads, some sort of locational attributes such as distances to water and those kinds of things. One thing that is missing in this data set is the slope, and which you can imagine is an important feature of where to locate these informal settlements. But in Bangalore, it didn't really matter. It happens to be in a plateau and the relatively even surface. But what we did is to calculate all these other kinds of features, such as variance in sizes of the buildings, the kinds of orientations of the buildings, and so on and so forth. And I'll touch briefly upon some of these features to give you a sense of what needed to be done. So first, one of the key sort of features that we thought would be useful would be to calculate edge density, which is about figuring out where the building edges are, and that gives you sort of an indicator of the number of buildings. And a standard way to do that would be to use an edge detector that you can see on the top left as an example, and that translates into the edge density of you detect the edges and then you calculate statistics at a neighborhood level. There are other kinds of neighborhood features that are important. Texture is one. Orientation might be another. There are various ways to do it, and these are relatively standard, though may not be readily sort of available in the remote sensing literature, but has been used in landscape ecology, has been used in city planning and other kinds of places. The neighborhood feature that is becomes very important is the lacunarity, which is about the spaciness between various land cover types. And we use both building lacunarity as well as the vegetation lacunarity once we have identified the buildings and the vegetation. All said and done, we run this through a standard machine learning algorithm. We use a gradient boosted trees for our classification. We identify about 2,700 or so neighborhoods in these different types of informal and irregular settlements, and there might be a few more than what the official estimates are. And as you can see from the right image, they're pretty well scattered throughout. And when you see these informal settlements on the ground, they're pretty, they vary in their characteristics, both in their physical characteristics and their social characteristics, on whether they actually have tenure or not, whether they actually have services or not, or whether what types of buildings and what types of roof materials and all that kind of stuff. So in general, we're able to relatively accurately classify these different neighborhoods into different types of informal settlements. And so one of the, One of the important sort of feature that becomes important is the road density that is an important predictor. Distances to water is another important predictor, and so on and so forth. And the accuracy of the model is about 84% or something like that, with a kappa of 0.6. We're not satisfied with this. We decided that machines are bad at in a number of things. It's good at doing simple things very quickly. We decided that we want to verify it against human interpretation of images, and we decided to use two coders. Undergraduates are great for this. They essentially went through each grid of half a square mile and hand-coded whether there's actually an informal settlement there or not. And the results here are quite instructive, I think. The two coders agreed somewhat, but they disagreed quite dramatically. One coder would actually identify informal settlements that of 2 square meters, whereas the minimum informal settlement another coder would identify as 600 or so. And the numbers also varied dramatically. One would identify in total of about 600, and the other would identify close to about 1,500 or so. So this is where you get into this idea about which is actually doing, which version of this of truth we should sort of work with. And that really depends on the interpretation by various coders, whether to classify a particular area as an irregular or regular settlement, but also as to what type of irregular settlement is. And there is a lot of variation between the coders as to how to identify and what to identify a particular neighborhood. So you get about a sort of a concordance rate about 0.4 or so between the two coders. And the problem though is concordance between the coder and the machine learning algorithm, and the concordance rate is much lower. So what we decided to do is that we don't need 2 coders, we need hundreds of these coders. And so we decided that we're going to sort of model our validation by some of the sort of inspirations from place pulse and picture power, and we built up a sort of a mechanism, a web-based mechanism that would actually ask people to see whether this particular area is formal or informal. One of the reasons we built a web-based mechanism is that when we showed our analysis to the field team that we have on the ground that is actually collecting household information, it was very hard for them to work in a GIS environment, and they couldn't actually give us feedback that we wanted to. And this is one way we thought we could sort of utilize their expertise without having to train them in a standard GIS environment. So this is still in beta, but I recommend that you sort of go out and tell me what all the problems there are in this. Unfortunately, I don't have time to demo those right away, but it's a simple test where you can click on an image and say whether it has informal or not, or which one is more likely to be informal or not, and so on and so forth. The expectation is that we'll take all this information, we'll take the sort of the credibility of the rater, of the coder, credibility of the machine learning algorithm, and all that kind of thing, and sort of put it into one big sort of number crunching exercise and update the probabilities that a particular area would be coded as formal or informal, or what type of formal, and so. So that's the ultimate end goal of this exercise. And finally, we do have people on the field that are actually collecting some information about what kinds of settlements are there. And there's a standard instrument that we're using, which also feeds into our analysis. So a brief summary is that this has been a very enlightening process. One thing that I learned from this whole exercise is that it is very hard to figure out what the boundaries of settlements are, and to tell people how to actually sort of say which ones are boundaries and which ones are actually neighborhoods, and how to actually create those edges. And those become significant in determining whether a settlement is formal or informal. informal. And that is going to be the next big challenge for us to tackle. Thank you.